It's me, the French guy with the terrible accent. In the previous video, we ended with a list of interactable actors detected, pruned of those that are hidden out of view of the player. For the third installment of this series, we are finally going to evaluate and select which one is the most likely to be targeted by the player. You can see the end result we will reach now, where selection is smooth, even for objects that are barely visible and buried below a pile of other interactables. I added a simple reticle to have a better visualization of the camera center, but this is out of the scope of this video. It was about time we went to this point, so let's go! So first, let's address the elephant in the room. The performances are now absolute garbage because I went completely crazy and overboard when adding some objects to illustrate something. This will be improved as we do some more filtering, but there are still 1024 instances of them, so I expect no miracle for this stupid setup. Right now we are performing a 1000 line trace on tick, so my CPU is understandably questioning my life choices as it cooks. Bottom line, don't do that in your game. Anyway, back to the topic. We are going to calculate a score for each of the detected interactables based on how close they are to the center of the screen, where the player is aiming, and how close they are to the character. In order to build a list of these objects, ranked by their calculated score, we need to create a simple structure S_interactable candidate. It will simply contain a float called score and an actor reference, actor reference. Let's now create inside the first-person character blueprint a function selectInteractable. It will take for input an array of actor references to evaluate interactable actors, and two vectors, detection location and detection direction. The output will simply be an actor reference selected actor. We add it behind the detect interactables at location function and connect the interactable actors references array together. Forward the world location and the forward vector of the camera to the new function. Let's open it. We create a local variable array of the structure type we created earlier, sorted interactable candidates. Just to be sure, we clear it at the very beginning of the function. Then we create a for each loop which will take the interactable actors array as an input. We add a return node on the completed pin and leave the function as it is for now. We now create a function evaluate interactable candidate. It will take for inputs an actor reference actor to evaluate and two vectors, detection location and detection direction. The output will be a boolean isCalled and a structure of the type we created that we will call interactable candidate. First things first, you know the drill, we check the validity of the input actor reference, and if it's not valid, we return true for isCalled and simply leave the other output blank. We will now calculate the angular score, which we will do using a little bit of trigonometry.
No, God!
Relax, it will be simple. When calculating the dot product of two normalized vectors, the result is equal to the cosine of the angle formed between these two vectors. When they are perfectly aligned, the result is 1. So in our case, we will compute the dot product of the input detection direction vector with the direction of the detection location to the actor location, which is simply the normalized difference between these two coordinates. We cache the result in a local float variable .productResult. We will now introduce a float parameter, detection cutoff angle, defined as a config variable, put it in the appropriate category, compile, and give it a default value of 2 degrees. This will define the angle of a cone starting from the detection location and going towards the detection direction axis, outside of which all the interactables from the array will be called. The idea is to keep only those that are close enough to where the player is looking at. We compare the dot product result we cached earlier with the cosine in degree of the detection cutoff angle. If the dot product is greater, it means that we are inside the detection cone and we proceed with the evaluation. If it is less, then we can call the actor with a return node. Let's draw a debug cone at the beginning of the select interactable function with the parameter we defined to visualize which objects will be retained for evaluation. We add a call to the evaluate interactable candidate function and get the isCalled output into a branch. We are going to relocate the printing of the actor name and the drawing of the debug arrow from the detect interactables at location function to the false output of the branch to check that only the objects inside the cone are being kept. Time to check the result. It's working, and we have removed a substantial amount of objects to evaluate, but we still have a frame rate worthy of a PowerPoint slideshow. It is actually not surprising because we performed the angular culling after having done the visibility check, so we are still doing line tracing for each and every one of these objects. To fix that, we need to change the evaluation pipeline to perform the visibility check after that angular culling. Let's backtrack to the detect interactable at location function, remove the check actor occlusion from location, and replace it by a isValid node. Now, in the evaluate candidate score function, we add a branch after the true node of the angular culling check, get an occlusion check node, feed it with the appropriate inputs, and connect the false output of the branch to a return node with isCalled to true. Let's check. You can see that we have significantly improved the FPS. It's still bad, but that's also because we are running on tick and we still have an obscene amount of actors to process. But it's much better. I'll still remove a lot of these actors. We have no selection yet, so let's go back to the function. Out of the true pin of the branch checking for visibility, we will calculate an angular score and create an appropriate local float variable for it. We take the dot product result that we cached earlier and feed it into an arccosine in degree node to convert it into an angle in degree. Since culling occurs at detection cutoff angle, this will be our zero value, so we divide our calculated angle by this value. Right now, our logic is backward, since the output value is 1 at the cutoff angle and 0 in case of a perfect alignment. We simply do a 1- operation to get the proper behavior and cache the result in the angular score variable we introduced. While we are at it, we will also do a distance score. We create a local float variable distance score, and for this one, we will simply calculate the distance between the player and the actor to evaluate. We will divide that distance by the interaction range parameter, so we have 1 if the object is at the very edge of the detection sphere, and 0 when the object is right in your face. Once again, logic is backward, so we do another 1- operation and cache it into the distance score variable. For flexibility, we introduce a new float parameter, angular score weight, that will allow us to do a weighted sum of the angular and distance score to obtain our final score. Let's give it a random value of 0.8, which means that 80% of the score corresponds to the angular calculation. We create a local float variable resulting score. Multiply the angular score by that weight, and multiply the distance score by 1 minus that weight. The sum of these will then be cached in the new variable. Finally, we can connect a return node with isCalled to false, split the interactable candidate output structure, and connect the resulting score and actor to evaluate variables to it. We are now done with the evaluate interactable candidate function. Let's go back to our select interactable. Before the debug text and arrows, we will cache the output structure of the function and simply add the calculated score to the display name to see the result. Let's compile and run. We can see that we have an individual score attributed to each interactable detected and that it is in the 0 to 1 range. However, it's going all over the place and nothing is sorted. For our custom structure, Unreal doesn't have any implementation of sort function, so we will have to do it by hand. Buckle up, things are going to get ugly. We add a for each loop with break and set our local sorted interactable candidates at the input. Through the loop body, we break the array element and compare its score to the score of the current interactable candidate we want to add. If it is smaller, it means that our new element is to be added above this one, and we have reached the correct index. So we insert into the sorted interactable candidates array the new element at the index, array index in the loop. After that insertion, we break the loop. Two cases will not properly work here. If the array is empty, the loop will be bypassed and continue through its completed output pin. This means that the first element will not be added. Same thing will happen if the element to insert is the one with the smallest score. Both can be detected and handled manually by checking if the sorted interactable candidates array contains the current interactable candidate. If it is false, it means that we are in either of these special cases, and we simply do an addition of the element at the end of the array. Let's get back to the initial for each loop that brought through our input interactable actors references array. We will drop the draw debug array for better clarity. If sorting is working properly, the best candidate to return will be the first element of the array. Let's check first that this is not empty. If it is not, we will get the first element at index 0, break the structure, and return the actor reference. And if it is, we return a blank actor. To check the result, we create a new for each loop that will browse through our sorted array. And we will relocate the print string on the loop body pin to ensure that sorting was successful. Back to our main event graph. We can now show which actor was selected by simply drawing a debug box that matches its boundaries. Finally, we are able to identify the interactable that is the most likely to be targeted by the player. Even the object that is at the bottom of the pile can be easily targeted. There are still a lot of room to add more flexibility, like using float curves responses for the scoring, which currently is only linear. But that's something I will keep for later when I will refactor the whole interaction logic into a dedicated actor component. Also, you may wonder why I bother sorting all the interactable candidates by score, since just looking for the one with the max value would have done the same result. Well, that's because it will allow a very easy introduction of an index offset for the implementation of cycling to the previous or next candidate in the list, which will be the topic of the next video. Stay tuned and check out the demo of Astinia, the dark fantasy game I am providing programming support to solo dev Mantos Lapas, the gyros-eating archon of oversharing credit with lazy me for 7 years of nerve-wracking development from scratch of a huge game without any prior knowledge. Although I'm doing these videos for fun, I sincerely hope it helped you learn a thing or two, and if so, I'm open to any feedbacks in the comment section.